Dear colleagues, my presentations entitled Calculation of deflagration appearance in reactive gas mixes flows in two-dimensional arrangements. In the first paragraph, we will discuss equation of chemical kinetics. Equation of chemical reactions can be presented as follows, where A eta, that is components of gas mixes involved in reaction, and B eta is products of reactions. Alpha and beta, that is stoichiometric coefficients of direct and inverse reactions. Speed of changing of concentration of gas mixes, that's eta per dt. F eta can be found by this formula, where speed of reaction is can be found by speed of direct reaction and speed of inverse reactions. Both of them can be found by formula of Arrhenius hypothesis. For preserving of non-decreasing entropy condition, coefficients of inverse reactions were calculated from equilibrium constant, where G eta is Gibbs potential. Results of numerical simulation of flow with deflagration and detonation essentially depends on what system of reactions and meanings of coefficients were used. One of the aims of present work is testing of different system of reaction and meanings of coefficients. Finally, was chosen 9 components of gas mix: molecular hydrogen, molecular oxygen, atomic hydrogen, atomic oxygen, water, and radicals OH, HO double, H double, O double, and azote, and nitrogen, N double, molecular nitrogen was treated. Components as argon, ozone, NO, NO double were neglected. The follow system of 11 chemical reactions were chosen. For numerical simulation of system of kinetic equation, we choose some model. Characteristic feature of hydrogen-air gas mix deflagration is appearance of sudden explosion after period of induction. In this induction period, concentration of radicals H, O, and OH slowly grows. Mass of radicals nevertheless stays small, and one radical component transfers to the others. This explosion mechanism is branching chain reaction, introduced by Semyonov. During process of branching chain reaction, these radicals many times initiate reactions with other components of the mix. Nevertheless, mass of these radicals components is small during the reactions, then almost fully disappeared in every time of the process. That's why methods of quasi-stationary concentration is treated to components oxygen, OH, HO double. Velocity of changing of these components concentration is equal to 0. For component H and component H double O double, two simplified differential equations is treated with using speed of WO, W5. Speed of changing H essentially greater than speed of changing slow components, molecular hydrogen, molecular oxygen, water. That's why equation for H and H double O double should be solved separately with the other time scale. In addition to the theory of Semyonov, in this paper, changing of H double O double also calculated as decision of differential equation. Because of this very component determines full process of deflagration and transition to detonation 1. This is two differential equation for atomic ash and ash double O double. This is we should equal speed of O double to 0, and from this relation we calculate by algebraic equation concentration of OH double this equation for O double. The other components of mix, molecular hydrogen, molecular oxygen, and water, are found from consequent equation of system 2 till 4. Transition to algorithm of branching reaction should be used if term F phi more than 0. In this case, decision of differential equation for hydrogen grows very fast. Mathematical model of gas dynamics for reactive gas mixes. In addition to kinetic equation, we should take into account gas dynamics of reactive gas mixes. This is system of equation for gas dynamics unknowns in integral form. We used conservative unknowns rho density, m vector m impulse, rho full energy for finite volume, and rho c eta density of components of gas mixes. This is additional unknowns to the system of gas dynamics flow in case of reactive gas mixes. And additional terms is source terms, where in the equations for components of density of gas mixes, we should use source term rho f eta, where f eta is speed of a chemical reaction. Full energy is has additional term of C eta H eta, where H eta is enthalpy of component of gas mixes. That is internal energy of chemical reaction. For this system of gas dynamics, we use nonlinear finite difference scheme. Nonlinear finite difference scheme involves a transition from conservative unknowns to characteristic unknowns. That is element of some TVD and algorithms. That is in short procedure of finding agent vectors and agent values of Jacobian df to dq. F is a flow of in equation of gas dynamics. We find agent vectors and agent values by methods of Roy Pikes without finding inverse to matrix A. And after this procedure, finding of agent vectors and agent values, we use finite difference scheme of Harten and finite difference of Chakravarty-O'Sher of third order of accuracy. This is formula for difference scheme of finite difference scheme of Harten. The next problem were calculated as an example. We have closed cylinder and we have initially hot spot in the middle of this closed cylinder. For investigation of structure of shock waves inside of this closed cylinder, we initially calculate reaction of methane and oxygen. This is simple one-stage reaction, and so we can find structure of shock waves. In these pictures, we can see vector of velocity of gas mixes and level lines of methane components of gas mix. We can see that initial concentration of methane 40%, diminution till zero for a short period of time. That is full stage of deflagration of methane in oxygen. Finding this structure of the flow, we can produce numerical simulation of hydrogen air mixes in two algorithms. In the first case, flow is closed in cylinder initiated, was calculated on the basis of full system of kinetic equation with Levin reaction from table 1. And for the second case, the flow in closed cylinder was calculated on the basis of model of branching chain reaction with two differential equation for hydrogen and N double, H double, O double, and all procedure of which algorithm we shall discussed earlier. During this, the second algorithm, we sometimes calculate differential equation for H and H double O double, and one time we calculate different system of differential equation for H hydrogen molecular, oxygen molecular, and water H2O. This is picture of flow with vector velocity of the gas mixes and level lengths of temperature and meanings of concentration of molecular H double. We can see that initial time of appearing of deflagration near the axis of symmetry of the cylinder. At the end, we can also calculate problem of initiation of deflagration from hot spot in the left side in channel with obstacles. In this flow appears shock waves, and these shock waves transition to detonation waves. Calculations were made on the grid, which were constructed by author's algorithm, and it shows that algorithm of branching chain reaction can be used for calculation of such a difficult problem. Summary: testing was provided of application of kinetic model of branching chain reactions for gas dynamics numerical simulation of initial stage of deflagration and transition to detonation for hydrogen air mixes. Algorithm was developed of two velocity calculation with small time step for one ordinary differential for two ordinary differential for H and H double O double concentration and subsequent definition concentration of other components of gas mixes and greater time step for numerical decision of gas dynamic system of equation for reactive gas mixes on the basis of TVD scheme Harten and Chakravarti-Osher. On the basis of this algorithm, numerical simulation of two test problems were provided. Initiation of deflagration from thermal spot and propagation of deflagration for isolated cylinder and one for axisymmetric channel with obstacle. Calculation demonstrate the applicability of developed algorithm for numerical simulation of initial stage of deflagration of hydrogen air mixes. That is summary, and that is all what I want to tell to you. Thank you for your attention, dear colleagues.